Good afternoon, one and all. Let me check the sound's going in. It is fantastic. Thank God for that. Thank you for being here, especially if you're here for the live session. Some of you obviously will take this on demand afterwards, and we appreciate that too. But we really appreciate you being here with the live show. A couple of instructions about this afternoon. First of all, I'm James. Nice to meet you. Hello, if I don't know you. Or if I do, hello as well. But a couple of instructions for this afternoon. First of all, any technical issues at all, just stay with that YouTube stream or on the hub page, and whatever happens, we will get back onto that stream as rapidly as we can. This is our 14th or 20th session. We haven't had any technical issues so far, so hopefully that won't be the case, but who the hell knows what the world brings. Secondly, folks, you can ask questions today. So we have a live chat bot down on the hub page, bottom right of the page. Go down if you want to ask a question. I'll answer that in the little intermissions and what have you, and bring your answer back to you. Hopefully, if I can't do it in the show, I'll email you afterwards and do that for you, no problem at all. Thirdly, I'll go over the instructions a little bit in detail when we first go onto the canvas, but I do want to stress that you really, really do need the notes pages for this session. Okay, so if you haven't got the notes page already, they're down in the description or they're below the video on the hub page. So I would strongly recommend that you do this session along with those, and I'll talk about other instructions when we shift over to the canvas. Finally, and then I'm going to ask a favour of you, finally, when I go to the canvas, we do have a microphone change at that point, so you might just have to tweak volume between camera view and digital pen view. So if you could just be aware of that, that would be great. Finally, and this is where I'd ask you a favour, guys, we're really looking to expand and build that YouTube sort of platform that we have and the prowess we can kind of show from there. So I'd be super grateful if in return for this completely free open source, all the resources to you session, if you could put a like on the video and if you could also consider to subscribe to the channel. We're trying to get up above 15,000 subscribers before the end of revision, and you guys can hopefully help us to do that. So do consider giving a subscribe on there if you're able to. Obviously it's a free thing, and it really boosts us and allows us to do more of this kind of work. Okay, I think that. Oh, by the way, there's normally two of us in the studio. I'm here on my own today because Marta, bless her, she's on her way, but she's flying back from Spain where she's been seeing her family for a little bit. So I'm on my own. So if anything goes wrong, it's completely my fault, which is nerve-wracking, but hopefully it will be straightforward. So what I'm going to do here, guys, is I'm going to switch to the canvas view. In terms of timing, we will absolutely definitely be finished at the very latest before 4:30, because at exactly 4:30 I'm doing another one of these sessions for the NCFE Health and Fitness Qualification Level 1 and 2. So no matter what, I've got to be there at 4:30, so we will be finished by then, but it might go tight. We will have a brief pause in the middle of the session just to do a little bit of a chit-chat, and then we'll move on to the second part. Okay, so there's a lot of content. We're going to cover a lot. Follow along. Oh, and a warning, guys, I'm going to draw. I can't draw for toffee, but live with me because the concepts are good ones. Okay, so I hope the drawing comes across. Okay, I'm terrified, but I'm going to give it a go. What the hell? All right, here we go to the canvas. Okay, my OCR GCSE friends, obviously we're on paper 1. Just a reminder, we're doing paper 2 as soon as your paper 1 exam is actually out of the way, and look for the dates for that. It will be worth it. That's a big session, that one. Anyway, what I want to stress in this particular part is we're looking here at working at more than AL1 or just knowledge. Okay, what we're trying to do here is we're really trying to develop the skills of your exam paper, and you'll see that as we go through. Now, with that in mind, the exam infographics are something that I would really recommend you have a look at. It gives you a very, very clear indication of the types of skills and the types of content that are really, really commonly expected of you in this particular paper. It also stresses to you some of the things that might be best for you to practice. So I'll just stress for you stress to you guys, for example, the importance of 1 and 2 markers on this paper. The exam infographics express that. Go and grab hold of them and they'll help you. Moreover, folks, you definitely want to take this particular session I'm doing now with the notes pages available to you. I'm effectively going to write on the notes pages you've got, so you need to follow along with those notes and to add your details as we go. Now, when it comes to the national mock exam, I really recommend that you attempt this, okay, and you have a go at answering that paper. Now, obviously, you can do it in a more kind of exam scenario or less. It's up to you. You can do it with your teacher or not. But the other thing is you want to sort of like really get to know the mark scheme that's associated with that, and specifically the model answers that we've written for each and every question is on there, including the 6 marker, okay? So that's something that we would really, really encourage you to have access to and have consumed and really learned from. I think that's... Make a point of going and learning from those resources, okay? Learn from them. I don't know how else to put it. Different people do it in slightly different ways, but if you do that, it's going to make a really significant difference to the outcome of how you perform in this paper 1. So learn from those resources. That's really what I'm trying to get across. Now, let's move this on a little bit. This is what we are, air quotes, covering in this particular show. There's 10 topics, the vast majority of which were on our national mock exam. And what we tend to do is we write the national mock, we do the analysis, we go, okay, this topic's always on, this topic's really important, this topic's asked this way, students don't do well on this topic. And then we write a national mock exam with those sorts of contents on them. And then what we do is we then make sure that we cover a really broad range of that in the actual session. Moreover, folks, again, we are looking today AO1, knowledge, AO2, explanation, application, examples, and we are looking at AO3. AO3 skills include analysing, evaluating, and a couple of other bits and bobs. So we're going to cover all three of those in this particular session, and that's something that I want you to, I'll probably mention it as we go, but also try and spot it as you see fit. And finally, guys, I think this is important. This is one show, okay? I'm doing one show for you now, but I've been doing this for a bunch of years, okay? And you've got 2022, 2023, and other sessions that are live on YouTube that cover different content to what we're going to cover today. So it's actually quite possible to go and cover a massive range of the actual course of paper one from our revision shows between 2022 and 2024. So I'd really encourage you to do that. And by the way, the theme's pretty much the same of how we do it, but there are, we develop it year on year, so there are slight differences. There's always notes pages, for example, though. That's something you should really benefit from. Okay, now, what we've got here is we really want to understand the different movement patterns at hinge joints and ball and socket joints. Okay, so obviously at hinge joints, we're talking about knee, we're talking about elbow, we're talking about ankle. At ball and socket joints, we're talking about the hip and the shoulder. By the way, I'm not going to talk a lot about the ankle, not broadly mentioned on this course in a lot of detail, apart from in the levers system, but just bear in mind that ankle is one of these. Okay, now rather than doing what's called a definition, now you might be expecting me to write flexion mean no. What I'm going to do here is I'm going to draw for you. So I'll get your drawing pencils out, folks, and we're going to have a go at this. Flexion, first of all, this is how we're going to draw it. First of all, what I'm going to do is I'm going to do flexion at a ball and socket joint. So I've got a little person here. We're looking at this little person sideways on. They've got arms here, they've got legs here, and they've got feet. Now, I'm not sure exactly how I've drawn that as a sort of a good drawing, but, nevertheless, that's what we're going to go with. When we get flexion at the ball and socket joint, guys, flexion involves the arms, that was meant to be a different colour, involves the arms coming to here. So my arms would now move in front of my body, that's my arms, and my legs would move in front of my body too. So the blue lines I've drawn on there, almost as if I'm going into some kind of pike jump on a trampoline, that is what we refer to as flexion at a ball and socket joint. That is flexion, nothing else. So at the hip, at the shoulder, this is flexion. Notice I am not bending the knee, I am not bending the elbows. That is flexion, and that's what we need to be aware of. Now, when we talk about things at a hinge joint, let me just use the same colours for this. When we talk about things at a hinge joint, so there's my ball and socket flexion, here's my hinge joint. What I'm going to do now is I'm going to draw this time just an arm or just a knee. So first of all, here's the arm example. Flexion would be when the humerus is like this, and here what we've got is we've got the radius, it's actually the radius, moving towards the humerus in this case. We have got the elbow effectively bending. When we'd be talking about the leg, the knee, sorry, we'd have the femur here and we'd have the leg back. This here, if that there, here's my little person, that there is flexion at the knee, okay, because the knee is bent. And it's really important that we can stress that. We are talking about different things. When it's a ball and socket joint, everything sort of stays straight, or it can do. So at the shoulder, at the hip, they go forward. At the arm, at the knee, we get bending, we get flexing. We would say the insertion moves to the origin. It doesn't matter in this case, but that's ultimately what's happening. So make sure you've got that clear. Now, extension, lovely, is a very similar scenario. So here's me little fella. We've got him here. Don't know why he's a him, but we've got him in his sort of natural position. God, what am I drawing? And what's happening is when we go into extension, the shoulder is kind of coming behind, the hip is sort of coming behind there, okay? So this is as if you look at that there, what we've got is got the arm behind the body, at the shoulder, not the elbow, and we've got the leg behind the body
at the hip, not the knee. Okay, that is what we mean by extension. That is extension. So look out for things like when we push off the ground to run and we push our leg back on the ground, that is extension of the hip, for example. When we perhaps start a bowling action in cricket and we put our arm behind us and it ultimately comes over, that is extension at the shoulder. When we prepare to throw a javelin, that is extension at the shoulders. So we're bringing our arm back and behind us. That is what we're talking about. Now, when we talk about this, that's a ball and socket again. When we talk about this at the hinge joint, now what we're going to get, here's my arm, and my arm, if my elbow is here, my arm is now straight. Okay, it's now straight. We have got this movement here. We've got extension of the elbow. Again, if I've got my little fella here, we come down, there's the arms, here's the hips. We are talking about the legs being there in extension. So my knee joint, which is this one here, is extended. We're standing up straight. We're standing up straight. That is what we mean by extension. Now, abduction is a slightly different sort of notion. So let me draw my little fellow again. We're look at him face on in the anatomical standing position this time. So here's me little fella. Okay, here he is. He's very basic drawing here. What's going to happen with abduction at a ball and socket joint is we are going to get, for example, the shoulder coming up to this position, the shoulder coming up to this position, the hip coming here, the hip coming here. In other words, we are getting movement away from the midline of the body. That is what abduction is. If I was to draw a midline there, I would draw something like this. There's the midline down the center of this person, and notice that those four joints have moved away from that midline. That is a cartwheel. That is a star jump. That is a diving save. Imagine that person is not upright but sort of going over to their left. That would be a diving save in hockey or football, or I don't know, a wicketkeeper diving to catch a ball or something like that. That would be what we would have in abduction. Now, the good news about that is we don't have abduction when it comes to hinge joints. It just doesn't exist. What about adduction then? Well, adduction, in fact, adduction is this. I'll tell you what I'll do here. Adduction, where are we? There you go. I think this is going to work. I'm going to take my little fella. I'm going to copy him. I'm going to paste him. See if this is going to work. It might not. I might have just embarrassed myself. No, it worked. Look at that. So take my little fella there. And what we're going to do now is we're going to bring the arms back. We're going to, at the shoulders, we're going to bring them back. We're going to bring the hips back. We're going to bring the hips back. And what we end up with is that adduction brings us back to our standing position. So when we're adducted, we are bringing everything back towards the midline of the body. Remind yourself, the midline is this point down here, okay? Effectively the vertical axis, the longitudinal axis. So there's midline. We'll bring it back. That is adduction. Now, circumduction, right? Imagine you're looking at a shoulder sideways on. So here's the shoulder. You're looking at it from the side, okay? Now, so we're looking at it from the side. This is forward, this is front, and this is back. By the way, I should have said, there's no, for adduction, there's none of that at a hinge joint. Now, this is our shoulder. Now, what would happen when we do circumduction is the arm would do the arm at the shoulder would do the following. It would extend, okay, so we'd get extension here, then we'd get abduction, then we'd get flexion, then we'd get adduction. In other words, the shoulder will rotate to go through all of the movements we've got above, and that will produce a circling action, okay? And a classic example of that would be cricket bowling. There are others, but let's go for that. Cricket bowling, where we combine this plus this plus this plus this equals this. And we get the circling of the shoulder in that way. And finally, guys, rotation. If I go back to my very original drawing, there's a couple of places where rotation is important. At a joint, not so much around axes. That's a more general point. So here's my little fella, McGee's. Here he is. He's standing here. There's my classic drawing. Now let's take the head, guys. The head, as you can know, this person can rotate the head and can look to the side that way, or can rotate the head and look to the side that way. That is rotation of the neck, okay? But, of course, that is not at a ball and socket joint. So I'm just going to get rid of these here. So let me just get rid of that. That is rotation. But that's not what we're interested in here. What we're interested in is this person taking, if we just sort of isolate, for example, this arm here, and we take this arm over here. So there's that arm. There it is. There's that arm. So we're still on ball and socket joints here, by the way. There's that arm. What we do in order to rotate this is we rotate around its own axis. Around its own axis. And that would matter if you put your arm out in front of you and you start sort of trying to turn your arm all the way around its own axis. That is rotation. And a classic example of that would be something like spin bowling, okay, where we create, especially leg spin, where we create rotations on an object as rotating. Now, in my sense, that is definitions of those movements, and you need to be able to look out for those. We'll go on to this in a few moments. Now, I know my drawing is rubbish. That is clear. I am a terrible drawer. Nevertheless, doing that hopefully makes you more familiar with this process. Now, with that, my notes have gone off. Hang on a minute. I've got my notes on my tablet and they suddenly disappeared for me. Not good. Anyway, let's have a look at this. Let's look at the knee then. We have got the type of joint as a hinge or ball and socket. Now, we, of course, know that we have a hinge joint here. Wonderful. So let's go for hinge. We've got movements possible at this joint. We know it's flexion, extension. Brilliant. Okay, let's have a look. We've got ball and socket joint. I'll just put B and S, which almost sounds a bit rude, but that's what I'm going for. B and S. What movements have we got? Well, we've got flex, extend. I'm just going to put here, we've got add and ab for add and adduction. And of course, what we've got here is we've got rotation. We've also got circumduction. Brilliant. So we've got all of those movements there available for the hip. All of this, I'm going to do my same little trick. All of this goes, if I take all of that there, and do it again. It's turned out well, isn't it? Copy, paste, beautiful. I can plimp that in there. It's the same, guys. Okay, so that works in the same way, the same movements. What I would stress, though, because we can sort of think, well, they're the same, right? No. If you actually notice the sort of like anatomy of this, that's really, really shallow, that socket there for that socket that we're talking about. I won't name them here. But if you look here at the hip, this is like the ball is like right inside the hip joint there, okay? So it's right inside. You might also notice that it kind of, the ball of the actual femur here actually sort of trunks out. I say trunks, actually called the greater trochanter, funnily enough, but anyway, that doesn't matter. Whereas this, it's like all in one line, and what that means here is that we get more stability in this example, and we get more flexibility and more mobility in this example, even though they're the same type of joint. Now, finally, let's look at the elbow. What do we have here? Well, guys, again, I do my old trick. I'll simply copy this, bum, bum, paste this, bum, bum. I think I might have pasted that twice. There we go. And okay, it didn't work. Fantastic. I knew I was going to go wrong. I knew that was too good to be true. But here we've got a hinge joint. And here, of course, we've got the possibilities of flexion extension. So it's really important that we get to understand that, folks. And back with regard to those rubbish drawings I did, that will hopefully give you a bit of an understanding of those things. Okay, let's have a look at the roles of muscles in movements. It's all well and good saying, okay, we've got this movement, we've got that, we've got this movement. Well, how does it happen? You can't, the skeleton don't just move, does it? I don't know why I've gone into that accent. I went off the working class there. What's wrong with that? Anyway, the roles of muscles in creating that movement of those joints. So let's have a look at this. We've got something is the muscle that produces movement. It's the agonist. You can say prime mover. Both terms are absolutely fine. In fact, let me put that in here. But you can say prime mover or agonist. Now, I want to make a further point here. It's not just the muscle that produces movement. This muscle, if it is contracting, then it is an agonist, okay, as long as it's working at that joint. We have our fixators that are not working at those joints. The antagonist is the muscle that, and this muscle always must relax, so it relaxes when the agonist is contracting. So our muscles are working in pairs. We've got a muscle relaxing to allow the agonist to do its work. And finally, we've got the something muscle help stabilize. And that something muscle is the fixator. Okay, so the fixator helps to stabilize the joint to prevent unnecessary movement. Fantastic. And we've got, for example, when we're doing something like bicep curl at the elbow. So by the way, this is when we're talking about the elbow. The elbow's moving obviously here. Well, what fixes that and secures it? Well, we've got the deltoid above that sort of holds that area in the correct position in order to do that. Fantastic. Okay, so let's keep it going. Let's have a look at our different movement patterns and how they operate. We have got here movement pattern, flexion at the knee. So this is that bending of the knee. I'm preparing to kick, for example. I'm doing a leg curl, that kind of thing. Which muscle is going to produce that, typically speaking? Well, we have got the muscle which is typically responsible for for knee extension are the hamstrings. In order for that to happen, the antagonist must relax, and that is the quadricep, okay? And I'm going to say again, this tends to be the case. Now, I'm saying tends because in the future, folks, you will learn about different types of contractions and how different types of contractions affect the agonist and antagonist. I'm not going to get into that today because I don't want you to have any kind of confusion going towards your exam study. Now, in terms of our sporting example, what would this be? Well, I'm going to say preparing to kick conversion in rugby. I'm going to go for. Okay, obviously there's others. I mean, lots of action. You know, the running action, it would be a really nice one. Let's take this further. What have we got here? Extension at the knee. Now, in essence, what we're going to do is we're going to sort of switcheroo this. So what I'm going to say here is we've got the quadricep, which is going to cause extension. Remember, straightening of the knee. And the muscle which is going to be responsible for allowing that and relaxing are going to be the hamstring group. Okay, so the three muscles of the hamstrings are going to perform that for me. Meanwhile, my sporting example of that straightening the knee, obviously I could say executing the kick, but I'm going to say I'm going to go for a front kick in, how do you spell that? Taekwondo. Guys, check my spelling. I may have done that wrong. Taekwondo, but that's a front kick in Taekwondo where the leg straightens to sort of kick to the midriff, I suppose, and doing it that way. Now, what about flexion at the elbow? Typically speaking, which muscle will be responsible for that? And that is the bicep. Now, again, it pains me slightly to teach it like this, but let's stick with it for now. So the bicep typically causes flexion at the elbow. The antagonist, that allowing it, relaxing while it occurs, is the tricep group. What would be an example of that flexion? Now, we could obviously say something like a bicep curl, but I'm asked for a sporting example here. So I'm interested in something where this would be more relevant. I'm going to say in judo, I'm going to say a judo pull. Okay, now I'm not going to get technical, but when you pull someone in, you are flexing the elbow. When you pull someone to you, you're flexing your elbows and you're bringing that person in a sort of a pulling action. I'm going to use that. It's equivalent to a bicep curl. And then, folks, finally, extension of the elbow. The muscle that typically causes that by contracting is the tricep, and the muscle that typically relaxes is the bicep. And our sporting example, I'm going to go here, any kind of throw, any kind of punch, because we are extending the elbow, we're extending the arm, throw, punch, this sort of thing. Choose your specific example. I could say a jab in MMA, or I could say executing a javelin throw. You know, make sure you're being specific with those examples, but that's what we're looking at. And I just want to remind you, those are typically the relationships that we would expect there to be. Okay, lever systems, brilliant topics, folks. Interesting topic too. So first of all, I want to go through, let me just go in a little bit further so we've got a little bit of clarity. There we go, that's better. So with lever systems, one of the things we want to be able to do is to classify levers effectively. Secondly, we want to be able to describe them and make sure that we've got clarity over what their components are and what have you. Now, the thing I want to sort of stress to you, no matter what anyone tells you, I'm just going to sip my tea here. Well, I'll ask you the question. Have a look at this lever, and this lever. Ignore the sort of the person and the sort of the body behind it, but just tell me how many components there are to each lever. How many does it need? Just have a look at that. I'm going to take the opportunity. I'm going to put my pen down. And I'm going to ask you just to think, how many components does it have? I've got a lovely cup of tea here, enjoying that. And I wonder how many you come up with. Did you say 3? Well, if you said 3, technically speaking, you are unfortunately not correct on that one. We need 4 components for a lever. And if anyone tells you otherwise, guys, you refer them to me, because that is absolutely a fact. So what do we need for there to be a lever? Well, first of all, we need, I'll do this in sort of, I'll just draw a lever over here. We need a long bone. This is called a lever arm. So you've got to have a skeletal feature, a bone. You've got to have a long bone. You know, in this example, we've got the radius. In this example, we've got the tarsus and metatarsus. In this example, we've got the vertebra. In fact, in this case, it would be the top of C2 vertebra. It doesn't matter. That's technical, but we've got a bone here. Okay, so that's component 1. Secondly, we need a fulcrum. Okay, that's typically a joint. Thirdly, we need an effort. That will be a muscle contraction. And fourthly, we need a load. Okay, and that can be various things. Now that is 4 components. So just have that super clear in your mind that with if any of those are absent, we do not have a lever. Okay, so there are 4 bits to this. Now, with that in mind, let's look at the different classification of lever. We've got a first class lever here. Let me just go to a darker blue. We've got a first class lever here. Lovely. Okay. Now, why is it a first class lever? It is a first class lever because the F is between the other 2 components. In fact, I drew one up here. The fulcrum is between the load and the effort. Okay, so that's why it's first class lever. How would we describe this lever? Well, first of all, the fulcrum is the neck. If we were to get really technical, we would be talking here about the joint between the cranium, specifically the occipital bone, and the C2 vertebra. Now, obviously, at this level, we're not going to worry about that, but we're just going to call it that. But the fulcrum is the neck joint. Get that really clear. The load is the head, the weight of the head, and the effort, the E, this is the neck muscles. Now, again, I could name those for you, but we'll just keep it nice and simple for now. So what we've got there is we've got those components ready in combination with the lever arm to cause a first-class lever to operate. And our sporting example would be something like preparing to head a football, for example. We could have, for example, I really like this one. Extending neck. This is when you sort of look back over yourself, like above you. Extending neck in a Fosbury flop jump. And if you're not sure what a Fosbury flop jump is, that is where that sort of high jump technique that you'll be aware of, where you kind of stretch your neck back and over yourself. It's actually the second thing to cross the bar after your first arm, and we would extend the neck in that situation. So that's what we mean there. Now let's have a look at second class levers, guys. Now we know it's a second class lever because we have got the load is between the other 2 components, in this case the fulcrum and the effort. Now obviously the lever arm is always in its same position. It's in technically there, rigid, solid. So we've got the load between them, so we've got a second class lever. Now when we think about the description, let's just do that again. The fulcrum here, now you can get a mark for saying the ankle joint, but really the fulcrum here is the contact point. And when I say contact point, it's between the ball of the foot and the floor. That is the fulcrum. The load is the body weight. And the body weight, if you're interested, guys, acts straight down the tibia. Okay, that's the center of mass. And the effort, what we've got here is the effort is the gastrocnemius muscle pulling on the Achilles tendon to cause this to pull upwards. Now, obviously, if that ankle goes upwards, we're going to point our toes and go into what I would refer to as plantar flexion, but let's say into almost like a jumping pose or a tippy toes. That's what's going to happen there. Now, what examples have we got? I'm going to say pointing, toes, and I'm just going to say in gymnastics, just as a general one here. That would be one. But just, guys, if we can just say any takeoff, I'm going to go takeoff in, I'm going to go long jump. Obviously, we could go for anything. We could go for jumping for a rebound in netball, for example. It doesn't matter. Jumping for a smash in badminton. It could be any jump that would do that, but I'm going to go for a takeoff in long jump. And notice I've said takeoff, because not the jump as a whole, it's that specific moment when we're taking off, basically speaking. Now, let's get into this third example, and literally the third example. Why is it a third class lever? Because we have the effort between the two components of the load of the fulcrum. Notice I'm not saying in the middle, I'm saying between. Because this, guys, there's the fulcrum, there's the load. This is not the middle, that is between the other two bits. Now, what do we have here? The fulcrum is the elbow joint, fantastic. We've got the load here is the dumbbell, that's easy, we can literally see it there in the image. And we've got the effort here is the bicep tendon pulling down on the radius. Now, a couple of things. I'm saying bicep pulling down on the radius via its tendon. That is because the bicep inserts onto the radius just here. So when it pulls, it goes and causes that sort of curling action, that flexion at the elbow. That's literally what it does. That's its mechanical purpose. So what would be an example of doing this? I'm going to say, here's a nice one for you. What about a goalkeeper catching a low ball? Okay, so think about a football goalkeeper sort of bringing a low ball into their chest kind of thing. What about also, we've got the bicep curl. What about prepping an uppercut? Okay, so what I mean by that is in boxing, in MMA, in these sorts of sports, when the arm sort of comes in, so you sort of punch upwards, it's preparing to do that sort of inside punch, as it were. So prepping an uppercut might be one that we have a look at. Let's keep going, folks. We've got mechanical advantage here. Now, there's actually different ways to define this. Well, there's only one way to define it, but the way I'm going to define it in this particular occasion is I'm going to say the following. It is when we overcome a large load with little effort. And that is a nice description of what at least some levers are for. Okay, that is with little effort. Fantastic. So we've got that definition. It's also the effort arm divide. In fact, I'm going to put it on the screen for you. The mathematical definition is the effort arm over the load arm. So I'm just going to put that on the screen for you, and I'll see that might make sense for you in a second. So what we're going to do here is just to identify what an effort arm and a load arm is. So what I'm going to do is I'm just going to draw a very basic lever for you. Okay, and I'm going to draw, here's my lever arm. Don't worry about which joint this is for now. Here is my fulcrum. I'm going to put my fulcrum over here. So there's my fulcrum. I'm going to put my effort over here. So there's my effort. And I'm going to put my load sort of here. Now you might be noticing already that what that joint is a second class lever. It's probably the one acting at the ankle. But this is where I want to take this. I want to show you something. I want to go, right, this distance here, this is what we call the effort arm. Here it is, the distance from the effort to the fulcrum. Fantastic. This distance here is the load arm. Okay, it's the load arm. Now what I want you to notice in this situation is that the effort arm is longer than the load arm, and that occurs, when that occurs, we get this thing, mechanical advantage. We get to overcome large loads with little effort. And is it a surprise that we find that at the ankle in the weight bearing part of the body? So if I say when EA effort arm is greater than load arm, we can overcome large loads with little effort. We can get increased force, but there's a trade-off. But these levers, they have low speed and a short range of motion. Okay, range of motion. Now, the reason I'm saying that is because, okay, brilliant. These second class levers have got mechanical advantages. They're fantastic. And there's our second class, obviously, there. They're fantastic at shufting stuff, right? You can shuft stuff and lift heavy things. That's why it's at the ankle. It lifts the body weight. And that, there's muscles down there, not massive, but we get to sort of lift the body with them regardless, because we can overcome large loads with little effort. However, that ankle joint, for example, is not super flexible. It doesn't have a wide range of motion, and it don't move fast. Okay, and in fact, the vast majority of joints in the human body, of levers, they do not have this. Okay, the vast majority the other way around. They have what we call mechanical disadvantage, not on this course, don't worry about it, but that means that they're flexible and supple and fast and dexterous. And actually, it's a nice sort of philosophical thing to think about. Human beings are kind of developed to be mobile and nimble and dexterous and flexible and to cover distances. We're not like a force organism, if I can put it that way. We're not like we don't have lots of mechanical advantage. What we have is like the ability to be nimble. We're better at this and this than we are at this. And that's actually an interesting thing to reflect, because our sporting world also reflects that. Okay, and I'm not going to go too far in that because it's too philosophical for a pre-exam session, but it's something that I would encourage teachers to perhaps discuss with students. Very brief pause. Okay, nice little sip of my tea there. Enjoyed that. All right, let's have a look at planes to begin with, and then we'll get into axes. Planes. Movement always happens along planes. Okay, make sure you've got that language correct in your mind. When we're describing it, it's movement along a plane. Let me show you something. For example, let's take our sagittal plane. We've got this kind of board or whatever, sort of cutting through the body in this way. And what we're describing here is any kind of flexion, any kind of extension. Now, there are other movements that move along the sagittal plane, for example, at the ankle, but I won't get into them here. So, for example, let's just go for the shoulder, right shoulder here. If this shoulder moves here, 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 it's flexion. Okay, but notice it's along that plane. It's moving along that plane in that way. If you imagine it's almost like glued to it, stuck to it, and it's moving along that plane that way. If we were to put this leg at the bottom back here, to here, that's extension of that hip, that would be along that plane. If we were to take this elbow here and we were to bend it into this position, that would be flexion of that elbow, it would be along that plane. That's what we're talking about with that movement pattern. So what would be sporting examples of these things? Well, we've got loads that we could use. Well, first of all, pretty much all of the running action is along the sagittal plane. That's nice. What about something like a somersault, or any kind of sort of forward or backwards rotation for that reason? But a somersault, I'll go for that. What about something like a tuck jump? A tuck jump is a really nice one. Tuck jump's a real classic move in gymnastics and trampolining, and it's along that sagittal plane. Now, when we're talking about the frontal plane, now we're talking about different movements. So let's sort of, we really need to concentrate on ball and socket joints here for our case. Let's imagine that we've got this shoulder here, it is starting to abduct here, 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 here. Can you see how that is movement along that frontal plane? So we have got abduction. Obviously, if this person moves them back, we have got adduction. Okay, so that is the movement patterns that we're interested in along the frontal plane. Now, the sporting examples of these are slightly harder, but if we were to go for, think about a goalkeeper making a diving save. Imagine this person kind of leaping off to their, going over here, leaping off to their left and abducting their shoulders to make some kind of really tip of the fingers save at the far post type situation. What about here? A cartwheel. Okay, classic example of this. And we also, one of the things we've got lots of dance moves that will be movement along this plane as well. Okay, so I'll just sort of generally leave that point there. And then finally, guys, let's have a look at the transverse plane, probably the harder one of this. This is rotation. And can I stress to you, yes, it could be the whole body rotating, but can I just come back to that idea that this arm here, it can rotate around its axis. Okay, and that is along that plane. So we've got rotation. So I'm going to say things like a twist. I'm going to say things like a pivot. Would be a nice one, pivot in basketball or netball. I'm also going to say a change of direction. That's a really nice one. Any kind of change of direction is movement along the transverse plane. Now that's all well and good, and I'm going to try and sort of be consistent here. Because what we're going to do now, in fact, let's keep that idea of movement along the transverse plane, because now I want to show you movement around axes. Okay, movement around axes. So imagine that these sort of rods are solid rods and they're attached to these people. What would happen if we start to rotate this rod in this way to that person? What would they do? Well, how do we describe the longitudinal axis? Well, it's from the top to bottom. That's fine. Nice and simple. Okay, it is when rotation occurs. So I want you to link together the longitudinal axis and the transverse plane. Those movements happen concurrently together. So what we're talking about here is, again, we're talking about a full twist, let's say in trampolining for argument's sake. We are talking about a pivot, let's say in netball for argument's sake. And we're also talking about a cod, not that one. with your chips. We're talking about sorry, I'm thinking about a fishing trip. Oh god, now I'm thinking about Gavin and Stacey. Oh no. Anyway, change of direction. Okay, change of direction. That is rotation around the longitudinal axis along the transverse plane. Now, where it gets annoying, folks, is that transverse now appears again. It's like, oh my god, and frontal appears again. Oh my god, it's so confusing, and it is to be honest. So let's have a look at this. What I want to do is I want to take my purple colour, which was my sagittal plane, and I want you to be thinking, which of these axes does movement along the sagittal plane relate to? If we were to move around, which axis? And it's this one here, of course. What we're getting, movement around the transverse plane would be flexion, would be extension. Now let me just prove that to you. This axis here is not the only transverse axis. I've also got one here, 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 here. So for example, imagine this person kind of starts to flex and extend their elbow. That is rotation around this transverse axis here. Okay, so that is flexion extension. So what are examples of this? Well, a bit like along our sagittal plane, we've got running, we've got somersault, and do you remember I mentioned tuck jump? We've got tuck jump. Now obviously use your own examples, that's absolutely fine as long as they're relevant. But here we're making those connections between the axis and the plane. Now I use green for my frontal, and now what we're going to get is I'm now going to get nice and green. Where's my green gone? Here we go. We're nice and green here. So we're talking about along here. So rotation at this point. We're talking about abduction, adduction. Okay, abduction, adduction. And here what we're saying is examples would be a rotation would be a cartwheel. Think about that sort of pivoting around. We've also got a diving save. We talked about that briefly before. And we've got our dance moves. So I just want to make sure you guys are able to sort of at least understand, even if you find it a bit confusing, at least understand the connections between those things. But I want to come back to this key point. Movement happens around axes and along planes. Now, just a little challenge for you, and this is, again, just getting a little philosophical point, trying to sort of ignite your enthusiasm for sports science and PE studies. If I was to tell you that every synovial joint, which is the joints we study, every single synovial joint in the human body causes rotation around an axis. Now, what that means is that you and I are incapable of moving in anything but circles and part circles. And if you don't think I'm right, wherever you are now, especially if you're in a group of people, like in the classroom, you teach whatever, try and do a movement that isn't a circle or part circle. And I'm telling you, you can't do it. Prove me wrong. Maybe I am. Prove me wrong, folks. Go investigate. Now, let's have a look at this. Movement on the sagittal plane occurs, I'm going to change that to around. Okay, so sagittal, okay, is around the transverse axis. Fantastic. Try and keep my colours consistent. Movement on the something plane occurs on the frontal axis. Well, I know that that is my frontal. And movement on the transverse plane occurs on, it should be, again, around, this should say around, and I'll go to my orange, the longitudinal axis. So we're just sort of combining those understandings. Lovely. Okay, fantastic. We're talking about gaseous exchange here and really about the respiratory system. So let's have a look at this. I'm going to tell you a story of gaseous exchange. Now, guys, by the way, I'm going to teach you this in the PE, air quotes, fashion, but I teach biology as well, so I do want to unite our learning and make sure that it unifies with what we learn biologically speaking as well. So just bear that one in mind. Now, here's stage one. We're going to tell the story. We're going to have air enters the lung. Okay, enters the lung, and what it does is it's going to travel. It's going to travel to an alveolus. Okay, so here's my alveolus. Remember, the plural of alveolus is alveoli, but here's my alveolus. You can see it there. So the air enters the lung, and it travels to the alveolus. Now, I'm not going to get into the mechanics of that. You guys know that that occurs almost through a bellow, through a mechanical muscular pump that changes the air pressure within the thoracic cavity, within the lung, and it pulls air in or pushes air out. So, I'm not going to get into that here, but hopefully you guys have an understanding of that. Now, that's stage one. Stage two, by the way, a lot of this happening simultaneously. Stage two, so don't really think about this chronologically. It's more of a story. Right, this air is containing the following things. It is greater than 20% oxygen. So there's loads of oxygen. So I'm going to start drawing. So we've got a ton of oxygen in it. Now I'm only, these, compared to this alveolus, I'm making these absolutely massive. So these molecules will be way smaller in relative terms. So I'm putting a bunch of them, and just trust me, I'm not going to get into them. I'm saying there's a lot. There's a lot more than I've just drawn in there. Also, they're O2s, so that molecular speaking, that we'd have more than just one circle. But anyway, just for now, let's just do it like that. So that air, what we'd say is it's got quite a lot of oxygen in it. But the other thing is it ain't got much. It's got greater than 20% oxygen, but it's only got, I think I always forget this number, 0.03% CO2. So there's like 1, 2. There's hardly any of that. Okay, so I'll just put like 1 or 2 in. There's me CO2s. So what we can do here is we can say this air has a high concentration. It has lots of oxygen. Okay, but it has a low concentration CO2. So it's got lots of oxygen in it. It ain't got much CO2. By the way, there's obviously loads of nitrogen and a couple of other bits and bobs in there too. Okay, so we've got that mixture of gases is now in the alveolus. But now we've got to go to stage 3. And stage 3 is my favourite bit. This is where me mates, me RBCs, me erythrocytes, I'm not going to get into the names of them. My RBCs form what we call a column. Here we go. Here's me column. Here's me RBCs. Look at those fellas. They are coming through it. Oh my word. Look at them. They're going like, this is our house, but you know what I mean. They're coming. Now I have not drawn them well enough because they're more disc shaped than I've sort of drawn them with my shaky hand. But they're forming a column, and notice they are the exact diameter of that capillary which is on its way around. So we've got a capillary surrounding this alveolus, and these red blood cells go, we're here, boys. Like, anyway, let me not take that further. There's no need. Now we've got a column, and what these guys have got is these guys have got a low. So let me write this out. They've got a low concentration. They've got a low concentration of oxygen, because that oxygen has been utilised at the tissue, let's say the muscle tissue, and they have a high concentration. They have a high concentration of CO2. So let me sort of depict that for you. Let me just depict that. So it's got very few kind of oxygens. Now I'm really bastardising this drawing because it wouldn't look like that. But with regard, I'll make them much pinker, these ones. With regard to my CO2, it's got lots of CO2s, okay? I'm going to draw them in groups of 4, and I'm not going to get into why I'm doing that, but I am. So what's going to happen here? Remember, these particles are all bouncing around. They're just bouncing around randomly. They have kinetic energy. They're just bouncing here, bouncing there. Now, stage 4, we're just going to sort of define our term. Stage 4 means we have a concentration gradient. We have a concentration gradient. What does that mean? Well, it means on one side in the alveolus, we've got lots of oxygen and less CO2. And on the other side, we've got less oxygen and lots of distinction between them. And the other thing we have is a ppm. Now, I'm not sure if you know what a ppm is, but you really should if you've studied any kind of biology. It is called a partially permeable membrane. Okay, in fact, we've got 2 of them. But anyway, our alveolus and the capillary wall, they're made up of lining cells. They're called epithelial cells, doesn't matter. But what they do is they're capable of allowing small molecules to pass through it. Okay, effectively, the gaps between the cells allow tiny, tiny little molecules to pass through, such as gas molecules. So these things are bouncing around. We've got more blues in the alveolus than we have in the blood. And guess what happens? They randomly go blup, 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 blup. Meanwhile, my CO2's bouncing back and it's going blup, 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 and what we then get is a net movement, and that is 0.5 here. What we're going to say down here is that O2 moves from alveolus to blood, because that is the gradient between the two things. You know, we've got more in the alveolus, so it's sort of bounced around, so more of it sort of passing that direction. And we've also got CO2 moves from blood to alveolus. Now, there's another detail here which is really important, folks. By the way, before I say that, when you read this, I reckon some of you will go, well, does that mean because it's moving randomly, some of them go in the other direction as well? Yes, that is exactly right. People never teach you guys this, But there are oxygen molecules that are going from the blood back into the alveolus. There aren't many, but they're doing it because it's moving randomly. There's a bit of a exception to that. But anyway, so yes, but what we're talking about here is the net movement, the total movement, the trend, the typical movement. Because there's millions of these particles, the general movement is the way I've just described it. Now, the other thing I want to mention to you is that we have got air coming in and out. In and out. That is called ventilation. Okay, we are so it's not just like we put air in that alveolus and then all the oxygen gets consumed and then it's done. No, that air's been constantly refreshed. Meanwhile, this column of sergeant red blood cells is constantly moving through this way. So that gradient that we mentioned here is maintained again and again and again and again. And that is how this works. And then finally, guys, what we're going to say over here is that my point 6, we're going to say that the red blood cells are oxygenated. Now, you obviously know the term oxygenated because you talk about oxygenated blood going through, ultimately through the systemic circuit or half of it. And then what we get is that CO2 is breathed out. So we get rid of that waste, the CO2 from aerobic respiration, we get out. And I just want to introduce you to one last point. I think a really nice way to think about it is about rate of diffusion, because that movement is called diffusion, of course. You guys know that really well from biology. But that rate of diffusion is kept good by having a really high surface area. We've got millions of alveoli, so surface area is high. Also, I said before, we've got ventilation. We're constantly breathing. If we get more air in and out, and again faster, that helps. And we've got a constantly refreshed blood supply. And that really helps to keep that rate of diffusion nice and high. So I wanted to tell you that story, folks, because I think it helps us to understand it. Short stop.
Whew, there we go. So part 1, how we do for time. Oh dear. So we're going to have a very, very quick intermission, then we're going to crack on. Well, I have one new shout out to give that's just come in, and one that I've been looking forward to giving actually. So the new one, first of all, the one I got past this from one of my colleagues, was for the guys at Hornsey School, just saying hello. Apparently there's some pizza on the go, pizza arriving during the to sweeten the deal. Good for you. Yeah, fantastic. I go, what do I got in pizza? I would tend to go, kind of like I tell you what I've been experimenting with recently, ricotta. Try that, ricotta and a bit of spicy kind of pepper and that sort of thing. Anyway, and also to Miss Anderson over in the East, if I can put it that way, Amy, I just want to say a massive hello to you and the guys there. I really, really appreciate you guys. I know you're tuning into a bunch of sessions as well. That's at Thomas Clarkson Academy, I should say. And yeah, really appreciate it, you guys being here. So hello, Amy. It's good to see you. I'm gonna embarrass Miss Anderson here and say that she's a bit of a role model for me. I think she's some combination of a brilliant teacher, especially PE teacher, and I happen to know she's really committed to her work and to her family, and I don't want to give too much away, so I don't know what she tells the kids, but her family at home, and is a great parent too. So I just want to say that. I hope that's reasonable to say. I don't want to embarrass you, Amy, but I think it's a nice thing to say to someone and tell them what your impression is of those people. Okay, now we're going to get straight into that second session, guys. I just want to sort of warn you, I think this will be quicker than that first half, but it may be at the end that I'm really quite brief because we don't have a massive amount of time left. So I'm going to line everything up now, and I'm going to switch over to the canvas, and we're going to get on with short-term effects of exercise. Hopefully this is going to work. Here we go.
Wunderbar. I don't know why that came out. Anyway, short-term effects of exercise. Remember, short-term, these are during exercise. Now, I'm not going to read those out to you. They're there. You should have actually already learned those by now. Remind yourselves of them. What I want to do is I want to take these things further, and I want to explain the explanation of these effects, why exercise does this. Okay, so let's have a look at this. Short-term effect. We've got muscle temperature increases. Why? Well, there's a couple of reasons. It's due to blood temperature. So we've got blood temperature, which is going up. Okay, this is sort of happening in concurrently at the same time, and we also have what's called the thermo effect. Don't worry about the terminology, but the heat effect of respiration. When we release energy, both aerobically and anaerobically, we release heat. Energy and heat are synonymous. They are effectively the same thing. I don't want to get too sort of technical about this, but when we talk about the release of energy, we're talking about things that will effectively activate particles. We're talking about something which is effectively a release of heat. So, of course, that temperature goes up. Now, what's the sort of the impact of this? Well, it causes the muscle to have up arrow greater pliability. So think of it like Play-Doh that you've kind of worked with your hands. When you get it, it's all cold. It don't move very well, right? Once you've warmed it up, beautiful. It's like you can stretch it and it won't break. And blah, 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 blah. And another way of saying that is we get increased extensibility. The actual muscle fibers can get longer. They not get longer in terms of growth, but they can sort of they can contract through a sort of a greater range. And you'll notice that because you experience that your joints loosen up and things like that. Now, heart rate increases. Why is that, first of all? Now, I'm not going to get into cardiac control. You can study that at A level if you're interested, or indeed at level 3 BTEC or Cambridge Technical. But why is this happening? Well, we've got an increased demand O2. So, of course, going back to what we've just had a look at, it could be that we're pushing more blood through past those lungs and then back around to the body at a greater rate. So again, that's really getting more oxygen. It's a greater demand. And because we've got a greater demand for oxygen, of course, this technically means we've got an up arrow, a greater demand for cardiac output. And remember that cardiac output is stroke volume times heart rate. So basically, we are being demanded more. So ultimately, our stroke volume goes up and our heart rate goes up. And also, we get more O2 entering the cell, okay? More O2 goes into the muscle cell for aerobic respiration. Now, stroke volume is pretty similar to this in lots of ways. So the effect of this, obviously, we've got a greater demand for oxygen. But the other thing is that when our stroke volume increases, what we're saying here is that we're able to do more work. So a greater up arrow, we're able to do a greater intensity of exercise aerobically. Okay, now I just want you to think about that a second. If we've got more blood being pumped faster and more of it, amount of blood leaving the left ventricle per contraction, we're able to do more work without going into that anaerobic zone. We're able to power it aerobically. And of course, that helps us because it helps us to delay fatigue or to prevent fatigue. Now, here, cardiac output increasing. Well, that's increasing because of that and because of that. So let's just remind ourselves that cardiac output equals stroke volume times heart rate. So if this has gone up and this has gone up, then obviously by definition this has gone up. And the key reason that happens is because we want to be able to do that. Okay, we want to be able to do more work, harder work, and do it predominantly aerobically so that we don't have to experience fatigue. Let's keep going, guys. Short-term effect, we've got redistribution of blood. Now, again, I'm not gonna sort of get too much into the teaching of this, but just to remind you what we're talking about here, we're talking about the vasodilation of vessels leading to the muscles, which allows them to open and to have less restriction to blood flow. And we're talking about vasoconstriction of vessels leading to other organs, let's say the liver, for argument's sake, and that's causing less cardiac output to go there, and it's redistributing blood over to the muscles. Up to about 80% can be typical. So this is in exercise, and 20% might go to the other organs. Now, when we go to rest, these values literally flip, and the opposite happens. And this is called, obviously, redistribution of blood. So why is that important? And that is because we need to get cardiac output to areas of need. So when we are exercising, the areas of need are our skeletal muscles. There are biceps and our triceps and our quadriceps, etc. And we've got to get blood to those areas. And therefore, this process occurs and leads that to happen. Obviously, you've got to think about that as well, that when we're exercising, that's with more cardiac output. So it's not only we're getting a greater proportion, we're getting a great proportion of the muscles of something far, far bigger. Now, I've made an actual mistake here, guys. So I just want you to do a little bit of scribbling for me here. I don't want this to say that. What this should say here is we get more oxygen to working muscles. Now, we've already touched on this, more oxygen to working muscles. And with regard to that, guys, I just want to make sure that we understand that. That means that we can do more aerobic respiration. Remember, aerobic respiration is where we release energy for movement. but we do so without creating any fatiguing byproducts like lactic acid. Therefore, we're able to keep going its long duration without fatigue built in. So oxygen to working muscles. This one here, this one should have said lactic acid production. Now, obviously, we produce lactic acid during exercise because we are doing anaerobic work. So what is the impact of this? Well, if it accumulates, it will lead to fatigue. It will lead to pain. Now, we can remove lactic acid as we're exercising, but we need to be able to, we need to be performing at a certain intensity. Now, the other thing is once we stop, let's imagine we stop, we also find that post-exercise heart rate remains high. So does breathing depth. So I'm going to say tidal volume remains high. And even sometimes our breathing rate. And what we're doing here is we're effectively removing that lactic acid. And a great way to kind of prevent this is to use a warm-up. Okay, warm-ups really help to delay the onset of lactic acid accumulation. And that will help a great deal. Okay, let's move on. I want to get now into our long-term effects of training. Now, again, we've got tons of them here, and the key message I want to get to you is you need to we've grouped them for you here. So here's our general ones. Here's our musculoskeletal, metabolic, respiratory, cardiovascular. Now, we're going to go through these, and we're going to sort of pick some out and choose which ones to write about here. Okay, so what I'm doing here is I'm making sure that if I'm asked about cardiovascular ones, I can talk about those specifically. So let's do the following. With regard to the long-term effects on the CV system, I'm going to go for, well, the ones I'm going to go for, let me choose a different colour, I'm going to go for decreased resting heart rate. Resting heart rate. So I've got a decreased resting heart rate because I'm training over months and years. So first of all, let's describe it. Well, it would be a heart rate below 60 beats per minute. We actually call this bradycardia if you're interested. And the reason this happens is because this is happening because we've got an up arrow, a greater stroke volume. So our stroke volume goes up and therefore our heart rate can come down at rest. And why is that? And I'm going to say it's because we have a stronger, and hang on a minute, I'm going to draw this for you, a stronger, that is meant to be a heart. We've got a stronger heart, butterfly, bum cheek, I'm not sure, but that's meant to be a heart. So because we've got a stronger heart, the stroke volume goes up and our resting heart rate can come down below 60 beats per minute. Fantastic. Now let's take things further. Let's have a look at the second one. We've got hypertrophy. Hypertrophy of what? Here we go. We've got hypertrophy of, oh, what the hell is that? It looks like a dead Pac-Man baddie. That's meant to be a heart. I don't know what to say, folks. I can't draw, but I do my best, you know what I mean? So the left ventricle of the heart becomes thicker, engorged, stronger, more powerful, more muscular. Fantastic. What does that mean for the heart? It means it can produce more force. Little nuance about the heart is it contracts fully every single time. So if we've got more muscle fibers, it can contract stronger. Brilliant. We get an increase in resting stroke volume. We've just mentioned that already, actually. And guess what we get? We get a decrease in resting heart rate. Oh, so lovely, so lovely, so lovely. Fantastic. Now, furthermore, let's just go into my next one. I'm going to choose a more happy color here. I should have done these in shades of red, really. I want to talk about capillarization. So picking this from the list above. What do we mean by capillarization? Well, nice and simply, it helps with this. We're going to have more capillaries at an alveolus. Now, given what we learned a few moments ago, that is really useful, an increased blood supply, in other words. And what that does is it increases the surface area. Now, you guys know surface area to volume ratios really, really well. And obviously, the better that surface area, the more efficient the exchange is going to be. Now, surface area goes up. We also get an increase, because of this, in the rate of diffusion. So diffusion happens faster. Gaseous exchange happens better because we've got more capillaries at the alveolus. Now, guys, can I stress that wouldn't only happen at the lung, it would also happen at the muscle tissue as well, so it's worth just bearing that one in mind. Let's keep going here, folks. What about the long-term effects on the musculoskeletal system? Let me pick three, and let's then see if we can explain them, or at least describe them. So here, I'm going to go for hypertrophy of muscle. Hypertrophy of muscle. So what happens? What's the description of this? Well, we get a bigger, what we call cross-section. cross-sectional area of a muscle. So just to be clear, if we were to take a sort of a cross-section of a, let me just draw a muscle over here. Imagine this is a bicep or something like that. So there's the muscle, down here's the tendon. I'll just sort of draw that in. There's the tendon down there. And basically, I've just cut this muscle over here, look. And we're saying what would happen with hypertrophy. Let me get back to my red. Here's my muscle before training. 12 weeks later, hang on. My muscle is now, my muscle's gone like this. And all of a sudden, my muscle has got a bigger cross-sectional area to it. Okay? And that is what we mean by hypertrophy. So just to be clear with that, big biceps, the gun, what is happening? That is what's happening. So we've got a bigger cross-sectional area, and very simple, guys. We get an up arrow. That was the wrong color. We get an up arrow, an increase in force production. That's what muscles are for. Muscles don't do anything but that. They produce force. They are amazing, but that is what they do. Their specialization, guys, biology, their differentiation. Okay, that's what we're talking about here. Now then, let's go to a different musculoskeletal. We've got an increased resistance to fatigue. Okay, brilliant. So the muscles are able to do more work, kind of, how would you put this, like more muscular endurance, I suppose. So think about what an Olympic, I'm actually going to give you an example. Think about an Olympic rower. An Olympic rower can repeatedly stroke the, make the rowing stroke without fatigue, okay? And that might help them, for example, row the second kilometre of the Olympic race faster than the first. Brilliant, they accelerate towards the end. Wonderful, they've got that capacity. Now, last one, I'm going to say, maybe this is musculoskeletal, I'm going to say up arrow, increased bone density. Now, bones, they're one of my favourite things, so I'm not going to have to hold myself back here. But the important thing is when a bone, remember what's happening here, guys, that tendon is attached to a bone. Okay, so when this thing pulls with greater force, that bone has got to be able to resist greater force. So we're also saying be able to withstand greater forces. That's brilliant. So they get thicker and stronger. But this is what I want you to be aware of, really. This is, anyway, I'm not going to get into this, but they get increased tensile strength. Now, you might not have come across that word tensile before. Teachers, you might not have. This thing here, it's got to be able to bend and flex slightly. Now, the reason I'm drawing it like I am, it looks like I'm just scribbling. Actually, that's how bone's constructed. So, because this thing is hollow, it has to be able to bend slightly, and it can't break, obviously. Sometimes it does. And that's called tensile strength, when it can kind of flex and resist forces and the bones become stronger. Also really helps with power transference, but I'm not going to get into that here. Now, let's get into our respiratory effects. Now, I know it's a little bit tedious, you follow me through here, guys, but hopefully it's going to be worth it. What do we have as long-term effects on respiratory? Well, we get increased strength of, I'm going to put resp muscles. Think about diaphragm, think about intercostals. These respiratory muscles, they get stronger. Why does this matter? Well, we get an increased change in air pressure in the lung. So because we can pull air in harder and push it out harder once we're at sort of high exercise, that means we get a bigger change in pressure. That means we get a bigger tidal volume at rest. But also, what that means is we can actually, in exercise, we can actually draw more air in. Now, the next one relates to that. I've got here increase in tidal volume. Remind yourself, tidal volume is how much air is breathed in and out per breath. And what that means is the effect of that is that we have a greater potential minute ventilation. Now, remember, minute ventilation is how much air you breathe per minute. So, of course, if each breath is greater, of course, you can breathe faster in exercise. That's going to mean your potential minute ventilation, which is the amount of air breathed per minute, will go up. Okay, and that's really great because then, of course, we've got that ventilation. Come back to that word from our gauge exchange. Our ventilation now is more efficient. We've got that concentration gradient working really well for us. And then, guys, finally, I'm going to say, obviously, this is all connected. That is our last one. We've got an increase in minute ventilation, more air in and out per minute. Fantastic. And therefore, what do we get? We get an increased diffusion rate. Fantastic. And therefore, we can do higher intensity work aerobically. Brilliant. There we go. All connected, aren't they? Isn't it smart? Now then, let's move on to here. Absolutely critical what we do here, folks. I'm just going to take the briefest of pauses here just to sip my drink. Hang on. let me tell you who these performers are, please. Laura is a gymnast. Laura, she does gym. Okay, good one as well. We have got here Josh. He's a sprinter. Okay, so sprinter. We have got here, just to sort of clarify this for you, we have got Kate. Kate, she's a triathlete. Really good one. British triathlete. Brilliant. We have got we've got Tom. He's a tennis player, recreational, just beginning. He's in sort of my age. There's Tom, tennis player. We've also got, trying to choose different colours here. We've also got Carlos. Carlos is a Paralympic basketball player. He plays wheelchair basketball, but I'll just put b-ball in there. That will do the trick for us. And who am I missing? I am missing Julie. Julie is a member of the amazing Australian national netball team, so she plays netball. Okay, so there are our performers. That's the reference I've made here on the screen. Now, with that in mind, what we're going to start to do is look at how we make examples of our actual competitive fitness. Now, I'm not going to go over the definitions of competitive fitness. You need to do that, folks. I don't know how else to say it. Make sure you know them, right? That's on you. And you need to make sure, because they're on the screen, get stuck into them. Now, what I'm going to spend my time doing with you is really getting these into high quality examples. So we have got Julie. Remember, Julie was our netball player. We have got agility, how quickly you change direction of control without losing speed, balance, or power. So our definition is great. And our example here is Julie has the ability to dodge an opponent netball, to get free and receive a pass. Now, that's okay, but I'm going to add to it before making an unopposed pass into the D. Now, the point I want to make here is that example is now sufficient for me to be really confident in it. Why? Because what I've done here is I've gone through 3 stages. I have given an example. I've given let me change color. I've given an example. I've gone through the impact of that example and the outcome of that example. I've done the EIO model. Example, impact, outcome. Example, impact, outcome. Example, impact, outcome. That is what making good examples in PE exams means. And by the way, if teachers, students, if you're interested in this model, I've got so many published resources on this, and things, literally grab and go things. Get in the blog, get stuck in. It's all there for you. Students, I've just also updated a blog post, which is the things to do in the week before your paper 1 exam, and it goes over this in detail. Now, with that in mind, folks, let's just analyse this. We have got Julie. She's got the ability to dodge an opponent. So there's my example, done, click. To get free and receive a pass. There's my impact, click. But I added the outcome before making, and look at this word, unopposed, like it's probably something that's likely to go well, isn't it? Pass into the D. And I said into the D because it becomes quite attacking, quite impacting, we're quite likely to score. There's my outcome, okay? Example, impact, outcome. Let's do another one. Just stick with agility for now. I'm gonna pick Tom. Okay, now Tom was our tennis player. Okay, so that's what we're going to go for. Sorry, I'm not going to pick Tom. Ignore that. I'm going to pick Josh. I'm going to pick the hardest one. Josh is our sprinter. Remember, agility, sprinting, they don't go together, right? No, they do, and we can do it in the same way. Let me show you. This is one of the hardest ones we could do. So this is about Josh, our sprinter. So Josh needs to move from, I'm going to put SS for sprint start, from sprint start position to upright running. So there's my example. In order to lead the race. So he wants to lead the race. There's my impact, lead the race. But here's my outcome. And apply pressure to opponents, because he's out in the lead and they're having to chase him down. So let me just go through this for you. There's my example. From sprint start up there. There's my example. Let me change color. Here is my impact, lead the race. Here, guys, and I know it's my dodgy handwriting, apply pressure to an opponent. Here's my outcome. EIO. Folks, that is the standard. Teachers, that's the standard. Okay, now a couple of others. Let's go and have a look at cardiovascular endurance here. Let's go and have a look at stamina. So let's look at who should we work with? Let's go for let's go for a hard one for cardiovascular endurance. By the way, I'm doing these sort of off the cuff. I'm going to go with Laura. Okay, Laura was our gymnast. Okay, so cardiovascular endurance that doesn't seem to go together. So I'm going to imagine her doing a floor routine. Okay, so what I'm going to go for here, I'm going to say it's in order to provide O2 to leg muscles. Okay, so there's my example. In order for her to recover between explosive tumbles so that the last one is powerful and spectacular. I'm not sure how I've written that, but my point is the following. We're doing cardiovascular endurance for a gymnast. Doesn't seem to go together, right? But what's happening here is I've got my example, which I'm going to do in my green, oxygen to the leg muscles. I've got my impact, which is effectively to recover between explosive tumbles there. And I've got my outcome, which I'm going to sort of circle in red, which is the last one is powerful and spectacular because she has recovered. Guys, that is the standard I want you to try to achieve. Okay, I want you to try and get to that level with your examples as you go through. Now, obviously, if I go through all of these, we'll be here all night. Okay, but teachers work with the students in order to be able to do this. Students, set that expectation of yourself and give yourself the opportunity to at least attempt to do that, because you're going to pick up a shed load of marks for that exact behavior. Okay, so we really encourage it. I'll just do one more. Let's do flexibility for flexibility. Who would this one be good for? Let's do flexibility for just realized I spelled Carlos wrong over here. Carlso. It's quite a nice name. Let's do flexibility for Tom. Tom's our tennis player. Okay, so let's say what would happen here. So he can stretch high at the shoulder when in first serve, in order to hit from higher position, ball position, and win more points on serve, which you could say, to hold his serve or whatever. But I've clearly gone for stretch highest at the shoulder, this first serve. There's my example. I've clearly said to hit from a high position, impact, so he can win more points on serve, outcome. I could have gone and said, so he holds his serve, he's got more chance to win, fine. But my point is I'm going through example, impact, outcome. Now, guys, that is the standard. And by the way, please do that in your 6 marker. Please, with little hands in that sort of praying emoji, like, come on, that's the standard we want to get to. All right, I'll stop banging on about it and I'll move on. Now, still on the same topic, we also need to think about the justify skill, okay? So, for example, justify the importance of one component of fitness to an athlete. And you could choose anything here. And the one we've got is we've gone for strength and we've gone for sprinter, Josh. Okay, so why is strength important? I think that's what we've gone for. And here's our example here. Maximal strength for sprinting. So let's just have a look at the justifications. We're making AO3 points here. Maximal strength causes large amounts of force to be applied to the block to cause an explosive start. So there's one explanation, which propels the sprinter forward faster. There's the next one. And the arms should allow the sprinter to pump their arms, causing greater forward motion. Again, I'm using effectively the same model there, but I'm making repeated justifications. Often when we're asked to justify things, guys, people will just give one answer. Now, if you're asked to give one justification, that's fine. But here I have made 1, 2, 3, and that is going to get me 3 marks. Okay, now again, you can repeat that process as many times as you need to for different performers, different components of fitness, different outcomes. Now that is great practice for you to go through. Now I'm sort of tempted to do one with you. Shall I do one with you? I think I'm gonna just on the basis of time. I'm gonna leave those there. Yeah. So we've got a scenario here, folks. We've got a volleyball player and they want to increase their leg power for jumping to make blocks, okay? And their muscular strength for spiking the balls. That's sort of upper body, right? And we want to sort of fill out the principles of training for this particular athlete. So let's have a think about it first. Our principle, first of all, is specificity. So we want to make it specific to this. So let's have a think about it. To the sport, we're definitely going to do upper and lower body here, because obviously we're looking to develop both those areas. So that's going to make it specific. We're definitely going to be working on the anaerobic system, because obviously we're looking at power and strength here, so that's really useful for us. But also, in terms of muscle groups, I'm probably going to do quite a lot of work on biceps for the biceps and triceps for the upper body, and we're going to work on quads and gastrocnemius a lot for the lower body to get that power. Okay, so we're going to do that. Also, notice when we get into kind of specific, because we're looking to do this for strength and power, we're probably going to do a combination of plyometrics and weight training to make it specific to those components of fitness, because the components of fitness are power and strength ultimately, so therefore we can make it specific that way. Secondly, folks, we want to think about overload. Now, overload is a really poorly understood concept in most cases, but the first thing we need to know is that it's a way of making training harder than normal to make adaptations. So how would we overload weight training? Where we would increase gradually, we'll come to that, the percentage of the person's 1 repetition max. Okay, that's what we would be doing. We would overload their 1 repetition max, and that, of course, would be the intensity. And I'll come back to the fit principle in a second, but just remember, this is fit. How else can we overload? Well, we could do, for our plyometrics, we could do more sets, we could do more reps, we could introduce another training method for type, we could train more times per week for frequency, and I'll come back to these points in a second. But this is how we're going to sort of overload and gradually make harder the session as we maybe pass through this 12 weeks or something like that. Now, let's take it further. We've also got progression. Progression is a very simple concept, and that is that when we do our overload, we do it gradually and steadily. So, for example, we are going to gradually increase the percentage of 1 rep max. We're going to gradually introduce more sets and reps. We're going to, and so on and so on and so on. That's what we mean by progression. We do it gradually, we do it steadily, we do it consistently. And also, if we increase intensity, we're obviously going to be careful not to, at the same time, increase time, for example. Now, we also want to be thinking about reversibility. Reversibility. The idea of this is that we want to prevent de-adaptation. So we're going to say, for example, minimum of 4 times a week. And why is that? It's because we're not going to have so much rest that things go back the other way. Also, we're going to think carefully about a range of methods. We're doing at least 2 methods here: weight training and plyometric training. But we could include some flexibility training, or could even include some fartlek or some intervals, something like that. Excuse me, a bit of a yawn. Oh god, that's not good. And then, before we get to the fit principle, I want to remind you of, I literally want to talk about the fit principle. So reminders. Oh, this is going to be difficult for me. We are talking about frequency. Okay, frequency. When we talk about frequency means how many times per week. Remember, we want to progressively overload that. We want to increase it as we go. When we're talking about intensity, in our cases, we're talking about percentage of 1 rep max. We're also talking about potentially percentage of heart rate max if we do something like fartlek training, for example. With the T, let me do this, I just realised it might be a bit like this. With the T, the time here, we are talking about this. What I'm prepared to tell you is session length. I won't get into that conversation. That we can make the sessions longer. Let me just leave that there. We can make the sessions longer. And in terms of type, we want to have nice varied methods. Okay, we want to have more than 1 training method. We want to have our plyometrics, and we want to have our weights. When we do our weights, we want to have varied lifts that we do. When we do our plyometrics, we want to work on different things. When we do our plyometrics for this volleyball player, we also want to be working on upper and lower body medicine balls for the upper body, for example. That's how we make training specific to that particular scenario. Now, everyone's favourite bit, let's get down to preventing injury. So a bit of writing to do here, folks, but we're going to do it quick. How injury risk can be avoided. So we want to talk about personal protective equipment, okay? And examples of this, we've got loads in sport, but think about things like shin pads, think about things like gum shields, think about things like scrum caps, For rugby. Think of, you could talk about American football helmets, I suppose. Think about, let me put cycling helmets. It's quite a nice one. So that's what we are talking about there. Also, we've got other ways. We can also look at correct clothing and footwork. So footwear, different blue, please, James. Clothing, footwear. Okay, so obviously having the correct stuff. So examples of this would be things like spikes to prevent us slipping, or studs obviously would be another example of that. We could also have cushioned for, especially if we're running long distances, cushioned shoes, for example. We could be talking about wicking clothing that helps to get moisture away from the skin and prevent us from being wet and getting cold when we sort of slow down and stop. We could be talking here about things like soft textures to prevent things like blisters and chafing. Okay, that's what we mean by clothing and footwear. We also want to be thinking about appropriate level of competition, so appropriate level of comp. Okay, so there's numerous ways to do this, but think about age groups. Think about gender groups. Obviously we've got scenarios, we've got certain sports like combat sports where men and women don't compete together, for example. This helps there to be parity, I suppose. Think about things like weight categories. These are really good examples, let's say in boxing, where effectively safety is enhanced in those ways. Let's go further. Let's also talk about lifting and carrying. Everyone's favourite, always reminds me of a certain scene from the original Office series, lifting and carrying, especially equipment we're talking about here. Okay, we're saying here things like when we do this, we need to have the load, what we're lifting, near our waist. Okay, so if we're lifting something, we need it near our waist, our core really. We want to keep back straight. Okay, things like this. Okay, no, I'm not going to go any further with that one. And also, can I just say generally, another one here is just a use of warm up. There's a use of warm up. That's a good way of reducing injury risk. Now, what we also need to be able to do, folks, I'll just sort of scoot into this last section here. What we also need to be able to do is talk about settings where injuries could occur and look at what possible injuries they might be. So let's go for a sports hall. What injuries might be likely in here? Well, we might have things like a hard floor. Think about how that might impact on falls, bangs of heads. There might also be litter. That can be obviously mitigated. Objects, benches around the side. There might be a lack of runoff area. Therefore, we've got to make sure that there is. We might also have lots of participants. So we might have collisions. Okay, these are things that need to be considered in the sports hall. Furthermore, if we go to a fitness centre, think about, I suppose here we're talking about some kind of weights, machines, gyms, that kind of stuff. Again, we've got an issue where we might have litter and debris. It doesn't tend to be the case, I found, personally. Number of people, obviously, that's about how close. What about this one? Proximity of machines and weights, banging into people. If you go to a cycling class, someone being really close to you, for example. We've also got the importance of replacing mats. Replacing gym mats, they get cracked and a bit sort of scratchy. We also want to be thinking about how we stack the equipment. That's going to obviously prevent things from falling on people, a weight falling on someone's toe, bit of a classic. Let's move things forward. We're at a swimming pool, obviously very obvious dangers here, folks. But what have we got as potential injuries? Well, we've got an environment which is slippery, so fall slips. I've seen loads of people fall over around swimming pools. We're talking about the possibility of loose tiles. This can cause damage to the feet. We're also talking here about places potentially being overcrowded. Now, I don't think that's a problem in and of itself, but people could jump on top of another in a swimming pool environment, for example. But it could also be that someone's struggling and then the lifeguard just doesn't see it because there's so many people. That's a bit of a problem. And then we've got sort of the idea of poor behaviour. Sometimes people will get a bit carried away in the swimming pool. Although I've never really understood the no petting bit. Why can't you have a little snoodle with your loved one? I've never really understood that in a swimming pool. I suppose it's a bit awkward for other people, isn't it? Let's just get on with it. And then in terms of playing fields, guys, Again, lots of you will be really familiar with this sort of stuff. I've made it sort of muddy brown here. Think about things like litter. Think about things like frozen pitches. Think about things like uneven surfaces. These can all cause twists and strains to the ankle, sprains even. And also think about safety access, because we're outdoors. How far is it to the nearest phone? I mean, obviously most people got a phone these days. How far is it from the nearest first aid kit? How far is it to the nearest warm place? These are safety access issues. And then last, we have got artificial outdoor. So Astro, tartan running track, something like this. What are we talking about here? Well, it's quite sort of grippy surfaces. So we often find that twisted ankles are a bit of a concern on these surfaces. We might also find something like burns, like slipping, and especially those older surfaces. The surfaces can be quite hard, so falling can be quite impacting. And also, because they're all weather, we often find ourselves playing in cold conditions where otherwise, things might be cancelled on grass or whatever, and therefore we've got that sort of knock-on effect. Wow, if you stay with me the whole time, fair play to you.
Whew. Well, guys, we are right on time, so I'm not going to stay very long. Thank you so much. I'm just going to check whether I've been asked to give any shout-outs or anything. We've got a really lovely one here from Onslow St Audrey's. Oh, guys, they're so lovely, the photos. I mean, poor you having to have me on the big screen like that. But it's so nice. Thank you for sharing it, guys. I really appreciate it. That's fantastic. Onslow St Audrey's PE department. Thank you. OSA_PE on Twitter. Fantastic. Thank you, guys. That's so lovely. It really touches me, honestly, and the guys I mentioned earlier on as well. Now, I'm going to play a little bit of music as an outro, but it's literally going to be a few seconds because I've got to be on another stream in less than 1 minute. I need the toilet and I'm not going to get to go, am I? Never mind. Guys, thank you so much. Don't forget we've got paper 2 available to you as well just after your paper 1 exam. I'm going to say it's in half term, check the date, I can't remember, but that's available to you, and I thank you very much for being here with us live. I hope it's been useful. Honestly, I really enjoyed doing this and I really appreciate that you guys attend, so thank you very much. Have a great one.